Hello everyone and welcome back. And in this video, we are going to look at the different types of packets using Wireshark. So basically, I have a lab, and that's where I'll be capturing some OSPF packets, and we'll go through. We will analyze them, right? And we'll see that how does hello packet exactly looks like, and how does DBD looks like, how does LSU or maybe LSF or maybe interstate request messages does look like, right? The objective of this video is just to look at the different hello packets which we already covered in the previous video theoretically, but we will go through each and every packet using the lab demonstration. So in this condition, if I look at the router one, I believe that OSPF is pre-configured on the router one. Okay, so we check router one, and on this router one, basically you can see in the diagram that there is a router one right here. So since we have the router one, some drawing to make it easier for you. So this is router one, and that's where the OSPF is pre-configured. So IP OSPF interface brief. Let me just display that. Yes, it's pre-configured. In fact, we can go ahead and we can enable the OSPF on its loopback interface as well. So now it should be enabled on loopback one, right? So then if I go to router 3, one more thing, that router 1 is already having OSPF peering with router 2, you can see. And also it has some information in its database as well. You can see that there are a couple of LSs in its database table, which is okay, right? And then if we go to router 3 now, right? From router 3, I have not enabled anything yet. So even if we go to router 3 here, so IP OSPF interface brief, there is no OSPF currently configured on this router. However, IP addresses are pre-configured. All right, there is no loopback interface created yet. Let me just create that quickly. So I have enabled that now. I have configured the loopback interfaces. So the loopback interface has got created now, and before I go ahead and enable OSPF on different interfaces of this router. So for example, I'm not going to enable the OSPF on Ethernet 0x1 because that goes towards router 1, as you can see here, right? I'm not going to enable OSPF on this interface, right? So let me enable OSPF on some other interfaces first before I get this enabled on Ethernet 0x1. So let me just go ahead and enable OSPF on 0x0, IP OSPF process 1 and area 0. Later on, like how to, probably you are already aware that there are two different ways of enabling OSPF on interfaces on Cisco routers, one using network command, right? And second, the command that I'm using here. So in this condition, I didn't configure the router ID on inside the OSPF, and therefore it will be picking up the router ID by itself automatically, and by default it's gonna pick the highest loopback interface IP. So we already created the loopback interface, which should pick that router ID by default. So for now, I'm not configuring the router ID manually. Just go ahead and get this enabled, get OSPF enabled on all of its interfaces, right? So I'll go to 0x2 as well. Go to OSPF enable, loopback 1, go to OSPF enable. So you can see that I have interfaces where I have configured OSPF. For configuring OSPF, I can see that OSPF neighborship is still not there because router 4 is not currently configured with OSPF, and downward also we have a couple of routers like router 5 and 6, but currently OSPF is not running on these two routers, therefore peering the neighborship will not come. So before I go ahead and configure OSPF over Ethernet 0x1 so that it can build the neighborship, right? What I'll be doing is that I'll start capture on Ethernet 0x1 like this. So let it start Wireshark, and once Wireshark gets started, thereafter I'll go ahead and will enable the OSPF, and then we will analyze the packet. So there is Wireshark, which is already running, right? Wireshark is currently running, and even we are receiving the hello packet, the OSPF hello packet. You see that, right? Because router 1 like at the end of router 1, the OSPF is pre-configured over Ethernet 0 by 1, and therefore router 1 is sending the periodic hello. Right? So you can see them, right? We are receiving those periodic hellos here on this link. So if you go and open up this hello packet, this is the Ethernet header. Obviously, the destination MAC address must be a multicast MAC address. Because destination IP is 224.0.0.5. So for that, the MAC address will be fixed 01005E. Like MAC address is starting with 01005E. Will always be a multicast MAC address, and then 00005 is translated from this multicast IP to the MAC address itself. Then we have the IP header, which contains the source IP, destination IP, and then of course it has the OSPF header first, as I discussed in the previous video, where we covered the theoretical concepts, and this is the content of the OSPF header, and then it has the hello packet, contains the subnet mask, hello interval, the options, right, and then it has priority, it has dead interval, it has TR router, it has PDR router. That's all there inside the hello packet. Let me just plot this out, right? And then I'll go ahead and we'll get this enabled, right? So I'll just go ahead over router 3, and on this router 3, I'll go to Ethernet 0 by 1, and I'll just say IP OSPF 1 area 0. And then let's go back to the Wireshark. And here you go. So we have LSR, we have everything, whatever we needed here, to discuss about the different patterns. I'm going to stop it now, right? Because the neighborship has came up now. You can see that it's already up, right? So let me see, show IP OSPF neighbor. Yeah, it's there, and it's in full state now. So I'm going to stop this capture, and we're going to analyze all of the packets now, right? So as we discussed before, that we're going to go ahead. I mean, we have 5 different types of packets. Like with hello packet is there in OSPF. We have DBT packets. You can see them, database description. Then we have linked state request, and we have linked state update, and also we have linked state acknowledge. You can see that we have all these different types of packets available. So during neighborship, like during building neighborship between these two routers, so basically we have router 1 and router 3, and we took the capture on router 3 is Ethernet 0 by 1, right? So we can analyze these packets. So look at the hello packet. So the hello packet, right, is multicasted. It is also unicasted, but if you look at that unicasted hello packet, right, that came from router 1 to router 2, and also one unicasted hello packet was sent by router 2 to router 1, and that gives the confirmation. Like for example, if I open that hello packet, for example, router 1 hello packet, right? So this is sent by router 1. The source is 13.1, which is router 1, and it is being sent from router 1 to router 2, and this time it is a unicast. But then look at the active name. I'm getting my own router ID. So router 3 is receiving this packet coming from router 1, right? So router 1 sent this unicast hello packet to router 3, and router 3 found its own router ID in its hello packet, which confirms that we have two-way connectivity. So this is just to verify the two-way connectivity, right? So router 3 has got confirmation now that my hello packet got delivered on the neighbor device. That's confirmed here, right? So it is a unicast packet. And also one unicast hello packet was sent by router 3 to router 1. So this hello packet, where the source IP address is 13.2 and destination is 13.1, this is sent by router 3 to router 1, and it contains the router ID of router. So it will confirm to router 1, like once router 1 will receive this hello packet, so it will be confirmed to router 1 that its hello packets were delivered over router 3 successfully. So all the parameters were matching, and thereafter you can see DBT packet. So this is the very first DBT packet that you can see here, right? That is coming from router 1 to router 2, and it is an initial DBT packet. In fact, if you look at the flag, like the OSPF header is going to be common as the hello packet. There will not be any differences. But then if you look at the this DB description, DBT packet, right? So it has flags in it, which means that it is an initial DBT, right? It will take some random DD sequence number as well, right? And it is also participating in master slave election, right? And then other DBD that came from router 2 to router 1 as well, right? So you can open up that DBD as well that came from router 3, sorry, not 2, router 3 to router 1. And it also had, all these flags enabled, like init, more, and then MS, and also it had a sequence number. But like any one of the router must be winner. So that will be router 3 in this condition. Like basically, first of all, router 1 and router 3 will declare themselves as a master router, but then there will be an election which will take place in between these two routers. And that is basically done based on the priority. So first they will compare the priority. If priority is common, then finally the decision will be taken based on the higher router ID. So first higher priority, then higher router ID. So based on the higher router ID, obviously this router 3 must be, therefore, router 1, like for example, router 3 got elected as a master router, right? So router 3 sent DBD packet with the sequence number, like we can see the sequence number, right? So the sequence number was 3512, right? And this was sent by router 3 to router 1. And then router 1 responded the same sequence number. You can see the 3512, the same sequence number, because router 1 agreed upon that, yes, you are a master. So now the slave, the slave device must respond back, must send the DBT packet with the exactly same DD sequence number that it received from the master. And that's what it is doing. And this time it is also containing some headers here. Like, as I said before, that DBD, like initial DBD will be bank DBD, and initial DBDs will be used for the master slave election. Once master slave election is completed, thereafter, inside the DBD, they will be exchanging kind of summary database, kind of LSA header, right? So you can see that there is a LSA header. It says that, okay, I have this LSA. It's not complete LSA. It is just a header. And there is one more LSA header. So in total, you can see that how many LSAs are there, right? So, and those are not complete LSA. These are just LSA headers, right? And this DBT is given by router 1 to router 3. And similarly, then finally router 3 is also giving one DBD to router 1 and saying that, hey, there is no more DBDs, right? There are no more DBDs. And also it has given its own LSA header inside it and says that, okay, I do not have anything else. And finally, the DBD will come from router 1 to router 3 saying that, okay, I also don't have anything, right? And there is no LSA header because it already provided all the information that it had in its database in the previous DBD. And then they are sending the LSR, like router 1 is sending LSR, link state request, to router 3 that, hey, I need this information, right? So you can see that this is LSR, link state request. If you look at the type, right? Message type, it's type 3, right? So type 3 is link state request, right? And also there is one LSR sent by router 3 to router 1. And it also says that, hey, I need all this information, right? Link state request. So I need all this information. And once they give in LSR to each other, thereafter you can see that update is coming in. Like router 2 is giving the update message, right? This is the update message given by router 2. Sorry, not router 2, it's router 3 actually. And also router 1 is giving the update message to router. You can see this is link state update, right? And it has so many different LSAs. And this time it contains the complete information. You can see that the LSAs are containing a lot of information. Like this is one of the LSA, right? And then it contains all of links information. It's cost, it's subnet mask, it's net ID, subnet mask, and then metric. All this kind of information is there in this LSA. So finally, in the form of link state update messages, both of the routers have exchanged their database information. And finally, you can also look at the link state acknowledgement, right? So if you look at this link state acknowledgement, right, one is given by router 1 to router 3, and router 3 has also given the acknowledgement back to router 1. You can see that, right? So link state acknowledgement will also contain the LSA header. Hey, I have received all these LSAs successfully. It was given by router 1 to router 3, and then router 3 is also multicasting the LSA acknowledgement. So router 3 is saying, hey, I've received all this information successfully. So that's that. So we have seen here that all those 5 types of messages were used by OSPF during the neighborship establishment. Later on, like other video, I'll cover that how neighborship comes up, which all are OSPF neighborship states we have. So that, thanks for watching.